have I? It's on. It's on. So your learning goals for circle theorems and proof. You'll recall key geometric rules and prior learning, including Pythagoras theorem. I'm assuming you'll know it. Angles and parallel lines, angle properties of common polygons. I've got a summary, which I'll show you in a second, but I'm assuming you know that stuff. It's not on the formula sheet, so you just need to know it. You'll establish circle theorems and the calculation of lengths or angles as well as proof problems, so we'll see some examples as well. And then there's also the language and notation when solving problems, but you've seen the proof language and notation. So this shouldn't be too hard. I've got that success criteria as well. If you're trying to work out what you know and what you don't know, that's designed to suit this, and it goes along with the proficiency scales that are on Passmark. So I'm just going to scoot down here. So I've just copied this straight out of a different textbook, and it's just all of the parts and the language that you'll need to know. I'm going to scoot through it a bit. I think you know most of it. But we have the centre of a circle, usually marked as O. The circumference of the circle, you know what that is, the distance around it. You know what a radius is, you know what a diameter is. A chord is a line that goes from one point of a circle to another point of a circle, but it's not a diameter. Although a diameter is a chord. It's just a particular special type of chord, but that's the chord, from one point to another point on the circumference. Once you have a chord drawn, then that divides a circle up into two segments. A small segment and a large segment, or maybe two semicircles if that chord happens to be the diameter. You have sectors. Sectors are like slices of pizza, so that's just made by two radiuses, and you'll have a small sector, large sector. So we might talk about sectors, and sectors produce arcs. So sectors are off arcs. Arcs are just part of the circumference. So if we've got this red bit here as an arc, and this is the major arc, so that's the minor arc between 2 points, this is the major arc between 2 points. Arc is language that will be used a lot in our circle theorems. Tangent, hopefully you know what a tangent is, but a tangent to a circle is a line that touches a circle at one single point and then continues on without going into the circle. So it touches the circle, doesn't go into the circle, that's a tangent, whereas a secant is a line that goes through the circle. So we won't really use secant too much. There is some circle theorems to do with secants. We might talk about them a bit at the end, but I haven't got anything to do with secants in your exam. And that's it. So I'm going to give you the 4 circle theorems. You are welcome to copy them down if you'd like to. They're pretty short, the first 4 anyway. And then we're going to talk about tangent theorems next lesson, but I'll probably finish the examples next lesson. Yeah.
Can we get these on the exam? These theorems?
No. So you need to, basically the situation is, I'm giving you only the thing from the external exam. I'm giving you the formula sheet that is the external exam formula sheet, because you might need to recall these for the external exam. Unfortunately, the external exam is on Unit 3 and 4, but there's no reason why they still can't give you a question that involves a circle in some way. So they are assuming all prior learning, including Unit 1 and 2, and for specialist maths, they're assuming all prior learning, which includes math methods. So you've got to know this stuff and be able to recall it. But most of them, you know, like for any of you who did extension last year, you know most of them. The first 4 are pretty simple and a bit obvious as well. So theorem 1 is the angle at the centre of a circle is twice the angle at the circumference subtended by the same arc. So that sounds pretty complex, but as a diagram, it's just saying that the angle off the same arc AB, the angle produced to the centre is twice as big as the angle produced to the circumference, anywhere on the circumference. So this would be the same. So that's a bit curved now. That's horrible. I'm changing that. So this will also be x here. It will be half of the angle at the centre of the circle. So if this angle at the centre of the circle was at 100 degrees, that would be 50 degrees. That's a circle theorem. A quick proof of that circle theorem, I'll leave it up there. A quick proof involves drawing that extra radius. So if you have this orange dotted line radius and PO and PQ, you'll notice here that PO equals, sorry, not PQ, PO equals RO equals QO, because they're all radiuses. And so therefore, triangle PRO and triangle QRO are isosceles. So that's going to help. That's equal to that is equal to that. And so if there are isosceles, then we get this angle is equal to x, and this angle is equal to x, and this angle here is equal to y, and this angle here is equal to y. I'm just defining those angles. Let angle P RO equal angle RPO equal y, and angle QRO equal angle RQO equal x. And then I think, hopefully you can see here, based on the angle sum of a circle, of a triangle, sorry, that angle ROQ is equal to 180 minus 2y. That's the angle sum of a triangle. And, oops, that should be angle, sorry. Angle ROP, and I've said Q, haven't I? So I'm going to change that to X, my apologies. ROP equals 180 minus 2y. That's an angle sum of a triangle. And so this becomes 180 minus 2y. This becomes 180 minus 2x. And so we can work out angle POQ, which is the angle at the centre, is equal to 360, because this is angles at a point, minus the other two angles, 180 minus 2y minus 180 minus 2x. And I put this as angles at a point equal 360. And that becomes 360 minus 180 plus 2y minus 180 plus 2x, which is just equal to 2x plus 2y, which equals 2 of x plus y. And hopefully you can see that x plus y is equal to 2 of angle PRQ. So that's that proof there. This is the most complex proof I have to do today, because I kicked this proof off, and the rest of them I can prove because of this proof.
And we'll
So,
have to prove that for every circle?
No, you can just use these theorems.
Okay.
I'm giving you the proof because you're in specialist maths, and so I assume you care about me proving to you that things happen.
Yeah.
But
an exam, we don't need to know.
no, but I might ask you to prove certain things in circle theorems, which will look like this. These will be your proofs. Yep.
Do you have to remember what theorem it is, like according to theorem 4?
No.
No.
I'm giving you an arbitrary list. So what you will need to be able to do is say, see how I've written here, angle sum of a triangle, which is a theorem itself, but I haven't given it a theorem name. So later on, you might be doing a question and you'll say angle at the centre equal to double angle at the circumference.
Or can you just draw a diagram and be like, because of that?
You pretty much could. You just got to give a reason that's clear which theorem you're choosing.
Because
Okay.
Insert
Yeah.
diagram.
And see, the problem is what you could do with me, you could say because of theorem 1, and I wrote the list down. But if you did that in an external exam, like every teacher might do it in different orders. So there's theorem 1, and that's the proof of it. I've just shown that this is 2x plus y and this is x plus y, therefore they match. Theorem 2 is this one. There's the cat empire symbol. It looks like a crown. But this is angles in the same segment of a circle are equal, sometimes called angles off the same arc. So this one up here you'll call angle. Well, actually, I'll show you the shortest hand you can do. I'm happy for you to do angle like this. Angle at the centre equals 2 times angle at circumference. So you can use that. That's the longest one you'll have to write. The rest of them are pretty easy. The second one here, theorem 2, angles in the same segment are equal. So all of these angles that come off the same arc are equal in size. And the proof of this is pretty easy. It comes from theorem 1, and that is that angle PRQ is equal to half of angle POQ, and this is the angle at centre equals 2 times angle at circumference rule. And I'm going to cheat, which you can't do in your exam, but I can, and just copy that. And I get, ooh, that's not what I wanted.
That's what you get for cheating, sir.
That's what I get for cheating, thanks. Karma, got me. Angle PSQ is also equal to half of angle POQ. That's PQO. And that's for the same reason. So I'll pop that down there. So what I'm saying is that this angle is equal to half of the inside angle, because they're the same arc, that's theorem 1. And this angle is equal to half of the inside angle, theorem 1. And therefore, angle PRQ equals angle PSQ. So they're off the same arc. And that will always be true. It doesn't matter where you draw it. I could draw it here, and they'll be equal as well, because it's half of that interior angle, the inside angle there.
So, like, if we had to write it, we'd say circle theorem angles of the same arc are equal.
Yes. So you could write it like this. Angles of same arc are equal. I'm not really worried about your grammar here, and I don't want you to waste time on this. So use the shorthand. Shorthand for angle, shorthand for triangle, where you can, but you do have to give me the reasoning. Okay? Generally speaking, a lot of the questions in the exam, for each time you do a step in a proof, it will be worth 1 mark. You'll get half a mark for making the correct statement and half a mark for your reasoning. So just expect that. You need to get that reasoning. So that's angle theorem 2. And I know I can see a couple of people writing it down, but I am going to move on. Angle theorem 3 is the one that a couple of people have already mentioned to me. And this is that the angle, if a triangle is inside a semicircle, it is a right-angled triangle. And this is really easy to prove as well, because the angle at the circumference is equal to half the angle at the centre, and if it's inside a semicircle, then the angle at the centre is 180 degrees. So half of 180 is 90. So this comes from theorem 1 as well. Proof. Angle, let me call this R. Angle, I don't want to use purple, do I? Angle PRQ equals half angle POQ. And here comes my cheating bit again. Paste that there. And therefore, it equals half times 180, which equals 90. I think this is the most basic circle theorem, and it comes up a lot. There's a couple other right-angled circle theorems to do with tangents. So you'll find that this comes up a lot with those to produce situations where you can clearly show certain things. So just keep that in mind and expect it to happen. So you can write this one down as angle in a semicircle equals 90 degrees. Or you could just write down angle in a semicircle. Same thing with angle sum of a triangle. You just write down angle sum of triangle. I don't need to know that it equals 180. I just need to know that you're using that idea. Any questions on that one? And Xander had made a point earlier. It is appropriate for you to draw a reasonable diagram. Like if you just drew, as you're reasoning, you just drew a diagram with an angle in a semicircle and had a right angled symbol, that would be alright as well. So I've got a couple of examples to do now. Calculate the values of x and y. Can anybody tell me? Example 1.
46 times 2 is 6 times 2 is 12.
Y equals 46 times 2, which equals 92 degrees. And I can do this again. Woohoo! There's my reasoning. And x, 46 degrees. And this is due to angles of same arc, or angles inside same segment, something like that. Okay? So that was pretty easy. You will get some, and you should find now, if you have a look through your practice papers, there's some pretty trivial questions, and I think I put a pretty trivial question in your exam as well. So know these trivial things as well. Example 2. Let ABCD be 4 points on the outside of a circle. Prove that angle ABC plus angle CDA equals 180 degrees. Here comes the moment. I'm going to cheat a little bit again because I know I'm not going to be able to draw a decent circle. And draw a circle like this. Does that look circular? There we go, look at that, amazing. And I'm going to put 4 points on the outside of the circle. Here, 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 and here, let's say, and connect those up. I've just randomly chosen them to be some sort of quadrilateral, which is all right, and I've chosen some garish colours there as well. A, B, C, and D, just arbitrarily name them. Prove that angle ABC plus angle CDA equals 180. So I want to prove that this angle plus this angle equals 180. Any takers on how we might start this?
When you say that ABC is the diagonal?
Well, I mean, if I connect them, that'll always be a quadrilateral, won't it?
No, because we might not be on the same point.
So what can I do to connect those? I need to connect those two angles somehow.
AC.
Is it that the, like...
Say that again, Max? Let's state where the origin is to start with. The origin is going to be really important. So if you're given a question without the origin, it's definitely worth having it there. And I'm going to draw this line to there and this line to here. Okay, the other two lines don't matter, but these two do. So what can we say now?
B is half of AOC.
So we can say, first of all, that angle ABC equals half of angle AOC. And here we go again. And what can we say secondly?
ABC is half
Of AOC again. Now we've got a bit of a problem here because we've got this double labelling of AOC. So what I might do, and this would be perfectly fine again if you recognise this in your exam. We've got a bit of a problem. I'm going to paste this here. What I'll do instead is I'll create an X and a Y angle, and I might just sort of put a line through that. Oh, actually, I shouldn't have done that. I'll leave it at that, and just put down half of X, and this one is half of Y. And that's fine. I don't mind if you even just cross it out and put that down. So once you realise, oh, we've got a bit of a discontinuity problem, I've got a one angle labelling two, then I think you should probably change it. And so what else do we know?
And then X plus Y equals 360.
And X plus Y equals 360. This is angles at a point. So you're going to say half of X plus Y?
Yeah, half of X plus half of Y equals 180.
And therefore,
Angle ABC plus ADC equals 180.
so you can see what we've done there. We've said that's what we needed to prove. Or I've called it CDA, but either way. This is half of that. This is half of that. Half of those two things added together is 180 because those two things added together are 360. Therefore, this plus this is 180. Yeah? And we've proven it. Now, I did that example deliberately because Theorem 4, the last one for today, opposite angles in a quadrilateral inscribed in a circle sum to 180. That's the theorem. That's called the cyclic quadrilateral theorem. So you can, and the proof is already there, you can call this one cyclic. I'm going to rub that out. I always forget the bracket is not my C. Cyclic quadrilateral. That can be your reasoning. So if you're making a statement that two opposite angles are supplementary. So this is an important word. You might see that word. Supplementary means that they add to give 180. Angle ABC plus angle ADC equals 180. And there's why. Under any circumstances, if you have a cyclic quadrilateral, i.e. it's a quadrilateral such that a circle can be drawn that goes through all 4 points, then the opposite angles add or sum to give 180 every time. Any questions? I might get through these. I'm going to do a couple more examples at least. I've only got 5, so I might get through them. And that takes the pressure off a bit next lesson. So example 3, find the values of m and n. This is pretty easy again. Any takers?
Because angles on three angles with n to make 180, which makes it 1.
So what I'm going to do is I'm going to introduce a labelling system again. Don't be afraid to do this. A, B, C, D. Don't fall for the trick here because it looks a little bit like these might be parallel, but they're not necessarily. But the setup that Alzani's produced there is very good. So we've got angle ABC equals 180 minus 120, which equals 60. And this is the angle sum, or actually I'm just going to say angles on a straight line. And angle ABC plus angle CDA equals 180, cyclic quadrilateral, and therefore 60 plus angle CD, or actually plus M is equal to 180, M is equal to 120, and N is equal to 130, same reason. Really, I should write out the reasoning for N again, but in the whole scheme of things, I'm not going to give you the same question twice in your exam. I would only ask you to find M, not then N, which is exactly the same question. So that's example 3. Any questions on that? That just used the opposite angles in a cyclic quadrilateral and angles on a straight line. Example 4, prove that if and only if the exterior angle of a quadrilateral is equal to the sum of the 3 opposite interior angles, then the quadrilateral is cyclic. So I'm going to draw a diagram for this one now. Let's say we have 4 points that make, I'll do those 4 points, a random quadrilateral there. And the exterior angle is the sum of the opposite ones. Yeah. Is that right? That's always going to be the case, isn't it? Exterior angle of a quadrilateral is equal to the sum of the 3 opposite interior angles.
It just means that
Oh,
it's
yeah.
equal to the interior angles.
Sorry?
Of the 3.
So the exterior angle is equal to these 3 here, the angles.
I'm just trying to
all
think.
of them
Because it's
on the
equal to
inside
360.
add up to 360, and then that one would have the opposite of it being a complementary for that one.
That doesn't tell me though.
The exterior plus the interior is equal to 360, and plus all 3 points inside are equal to 360 minus that.
I can't say good, but like, yeah.
I actually feel like I've written this one down wrong. I think if we can prove that this angle, no, that's not 180 then. 180. We can prove that this angle here is equal to this angle here, then that implies a cyclic. So if you show all 3, yeah, okay, no. I'm going to look that one up because I actually feel like I've taken that from somewhere and I feel like it doesn't work.
Yeah, he's saying that is always the case. It doesn't mean that it's cyclic.
Go.
The interior, like the left interior angle, set it as x, and then say that at the exterior of that, we have to just like set that as x. The exterior of that plus x is 360.
Yep.
Point. And then 3 interiors plus x is going to equal 360 because it's quadrilateral.
Yeah, we know that. Well, what he's wondering about is how does that prove that it's cyclical, the cyclic?
Y plus x equals 360 and also x plus
Yeah, that's always the case though. It doesn't have to be
z1,
cyclic for it to be.
let's call it theta.
That's what he's talking about. Again,
Yeah, this is my concern.
Oh, I see what you're saying.
yeah, it's always the case that it's not just for something.
I've collected these examples from somewhere and I've not really thought about this one as much as I maybe should have. X, and therefore y equals theta 1 plus theta 2 plus theta 3. That's always true. In actual fact, to prove that to the quadrilateral is cyclic, you have to show that this angle is plus this angle equals 180. And for those two angles, there's two opposite angles here, x and theta 2 to equal 180, then that would be the case if the external angle here was equal to theta 2.
Yeah.
That's what I'm not liking. So if the external, this is usually the exterior angle here, that angle, or this angle here, they're equal. So that, if you can prove that's theta 2 and that's theta 2, or either way, one or the other, so the exterior angle here that's created by producing that line, or producing this line adjacent to x, is equal to this opposite angle, then that proves those two add up to 180, so therefore these two are equal to 180, and therefore you have a cyclic quadrilateral. Because it's given if these two add up to 180, then these two must add up to 180. So you definitely have a cyclic quadrilateral. So I'm going to hunt down where I get that question from and see if I've written it down wrong. But either way, that's a good chance for us to talk about that exterior angle. So if you can prove that this angle is equal to that angle, that will only happen if it's a cyclic quadrilateral. And the rest of it doesn't quite work. Example 5 is the last one. And to be honest, actually what I might do with example 5 is I might leave it up now. You can go on and do some work, and on Monday I'll finish example 5 with you, and I will have checked up example 4, and then we're going to start tangent theorems. I'm sorry. And Monday, I'm not going to do that on Monday actually, that's a complete lie because we don't have a lesson on Monday. We've got a public holiday Monday.
I'm sorry.